not really, of course, one of them's moving, the other's not. This is a lot like a word problem that we did. We'll give ourselves a reference frame, up, down, right, and left. I'm going to make right positive and left positive and right negative. I'll make down negative and up positive. But I want to have this be cart A and this be cart B. And cart A is loaded up with masses. You can see that it's loaded up with masses because there's cylinders sitting on it. And I want to just say that I went to an electronic balance, and there's a video posted. If you want to watch it later, you're welcome to. But I went to an electronic balance and I measured how much mass A was. It was 1.811 kilograms. You can tell that this is actual lab data because it's a weird number. That's how much it really was, okay? I'm not like just blowing smoke or whatever. That really was, like, I did this, okay? The other one, mass B, 0.510 kilograms. And cart A was just sitting there, 0 meters per second. Cart B was rolling along at 0.39, 0.39 meters per second. And it was traveling to the left. Now, how was the data for the motion captured? Using a sonar motion detector. That's all it was. Okay, so things that you've used before. In the after situation, I'm not going to fill anything more in the before situation, because in the after situation, the motion sensor picked up the motion of these two objects. The after velocity for the heavier cart was 0.13 meters per second. And I got that by finding the slope of a position time graph. Okay, I didn't read it straight off the velocity data. It came from the slope of the position time graph, and that was to the left. So we've got a reference frame up at the top. And then cart B actually recoiled. It rebounded at 0.20 meters per second to the right. Now, what I'm going to ask you folks to do, because I have total trust that given enough lab equipment, you guys could make these measurements. All you have to do is have motion sensors pointing at two carts that were in a car crash, basically, right? So this is something that's very achievable in terms of collecting the data. But what I want you to do is, I've got an organizational table here. I'd like you to figure out what the momentum for each individual mass was before the collision, what the total momentum was before the collision, what the momentum of each individual mass was after the collision, and the total after the collision. But then again, even though it's not in the organizer, I'd like you to find EK before and after for the system. So when I say the system, I mean EK total and EK total primed. Find the kinetic energy before and after. And then I'd like you to take a look down here. I want to talk about percent efficiency. How could we analyze this? Well, percent efficiency compares energy before and after. Oops, that's not how you spell before. That's like some sort of strange alternate dyslexic universe. Oh man, and now I'm thinking about before because of the number 4. Anyway, before and after. And then there's percent difference. That compares two observed values in the same scenario. And then there's percent error. And that compares a result to a theoretically accepted or generally accepted value. Now the formulas for these guys look kind of similar. Percent efficiency, and maybe is the most different. Percent efficiency is, I'll just write it as percent EFF, I know that's a weird way to write a variable, is equal to energy final divided by energy initial times 100%. That's percent efficiency. Percent difference is value 1 minus value 2, absolute value of that, divided by, really it's the mean of value 1 and value 2. So I'll write that out, but it's the mean of value 1 and value 2. So it's value 1, I'll just write it as val 1 plus val 2 divided by 2. But the mean of those two values, that's percent difference. And then percent error is the measured value minus the theoretical value, absolute value of that, divided by the theoretical value. Oh, and you know what I forgot to say for both of those guys? Just so that I'm not squeezing it into the margin, I did it for the percent efficiency. I forgot to multiply by 100%. Sorry. So the first one looks like the way you would calculate a mark on a test. The second one is about how far two values are apart from each other, and then we define the mark on the test, if you like, as being the average value of those two. So it really is a comparison of those two things. And then the last one, we consider the mark on the test to be the theory value. And how far are you away from the theory value? That's what we're calculating with these three different things, okay? Now what you guys have to decide is, when I look at these values, and you're going to have a momentum total and a momentum total primed, an EK total and EK total primed, I want you to go through the thought process. If you've done this experiment, in the post-discussion, how would you analyze it? Would you go back and would you compare EK and EK total and EK total primed using which of these percent comparisons? Would it be a different percent comparison than how you would compare the momentums? And how would you choose? Does everybody understand the assignment? That's it, okay? So first do the math, then decide how you're going to compare, and then we'll talk about it, okay? That's it. Go.